Back, we're now going to do Physics Bootcamp Addendum Problem 14. Problem 14 is going to be a quantum mechanics question. It says, draw the Schrodinger wave function for a particle in a closed box with length L for the first 4 states. And then it asks you some questions about that. A, what is the probability that the particle is in the middle of the box in the second state? B, what are the most probable positions of the particle in the n equals 4 state? C, if the energy of the ground state equals 10 mega electron volts, what is the energy of the third state? And then D, calculate the actual energy in the third state. In order to do that, the problem tells us that the mass of the particle is 3.2 times 10 to the minus 29 kilogram, and then the length of the box is 0.5 microamps. Okay, so this introduces us to the concept of quantum mechanics, Schrodinger's equation, and also the easiest applications of quantum mechanics, which is a particle in a box. What are the likely positions of a particle in a box? And we're going to assume that the box is impenetrable. Okay, so this is one of the most common applications of Schrodinger's equation. Okay, so for now we are assuming that it is an impenetrable box. Okay, so the potential energy is infinite on the sides of the box. So let's talk a little bit about this, and then we'll get to solving the problems. When we look at Schrodinger's equation, this is the time-independent Schrodinger's equation. We'll see something like minus h bar squared over 2m, the second derivative of what is known as the wave function. This usually we use the symbol psi, Greek letter psi, times the potential energy times psi is equal to the total energy times psi. This is known as the time-independent version of Schrodinger's equation. Basically, this equation is an expression of the conservation of energy. We know from mechanics, kinetic energy plus potential energy equals total energy. Kinetic energy is half mv squared plus potential energy is equal to total energy. And then most often in higher level physics, we express this kinetic energy this way. We say linear momentum is equal to mv, and then v is equal to p over m. So we express this as half m p over m squared plus u equals E, and then we write this as half p squared over m, and then it becomes equal to this. So whenever we are studying the mechanics of a particle whose energy is conserved, we can say its kinetic energy plus its potential energy is equal to its total energy. Now when we express this particle as a wave, and then these functions P, U, and E become what are known as operators, okay? The particle in a box will be something like this. Length starts with 0 and L. Potential energy at the boundaries of the box is infinite, and then outside the box is also infinite. That means the particle has no probability of being found outside the box, okay? So what are the solutions of this equation to that kind of a situation? Well, we're assuming inside of the box there are no external forces on the particle. The particle can go back and forth, bounce off the walls of the box, and do whatever it wants to do. So the potential energy is 0. Okay? The solutions of this equation turn out to have this kind of a format. A sine of kx. Okay? The reason you can kind of make sense out of this is that you can say, well, if the wave function is a sine, its second derivative, its first derivative will be a cosine, and then its second derivative will be a sine, and therefore its second derivative will be proportional to itself, right? The next thing that you do here is enforce certain boundary conditions. These are very important. Boundary conditions. So what are the boundary conditions here? Well, we know that the particle has no chance of being outside the box. At the edge of the box, the wave function must be continuous. So since the wave function is 0 outside of the boxes, therefore right at the boundary of the box, the wave function must also be 0, right? So we say psi of 0 is 0, psi of L is equal to 0 as well. So if you put here 0, of course you're going to get 0. If you put here L, what does K have to be? Well, you say A sine of KL, right, has to be equal to 0. Well, okay, how is that 0? Well, basically it's 0 whenever KL is some multiple of pi. So we'll say pi n. When n is equal to 1, right, then KL will equal pi, sine of pi will be 0. When n is equal to 2, then you'll have KL will be 2 pi, sine of 2 pi will be 0, and so on and so forth, right? Therefore, K has to be equal to pi n over L. So the summary of that is what? The wave function has to be A, this is the amplitude of the wave function, sine of pi n, that's the K, pi n over L, x. Okay. Now, it turns out that when you study wave theory, this form of a wave is a very common form of the wave. You have sine of kx, k is known as the wave number, okay? And then that's equal to 2 pi divided by the wavelength of the wave. So this is a common parameter. And the units of the k are meter to the minus 1 power, okay? So this would be 2 pi, and then the wavelength would be meters, so it'll be meter to the minus 1 power, okay? So now, if you set this equal to 2 pi wavelength, we set this equal to pi n over L. Since we found that the K must satisfy that condition, what do you get? Pi and pi cancel, and you basically end up getting what? L is equal to n lambda over 2. So L went over there, lambda went over there, so you have n lambda divided by 2. You will recognize this from string resonance theory. When we talked about string resonance in a string, we said what kind of frequencies resonate in this. And we noticed that half a wavelength resonates in it. Lambda over 2 is equal to L. A complete wavelength resonates in it. That's lambda is equal to L. And then you have 3/2 of a wave resonates in it. And then our conclusion was that in that kind of a string, the condition for resonance was what? N times half of a wavelength was equal to L. In other words, you had to be able to fit integer multiples of half wavelengths into the length of the string. Well, the analysis of the particle in the box situation comes out to be exactly similar to that. The length of the box, instead of the length of the string now, the length of the box must be integer multiples of a half a wavelength. You see n? You have n is equal to 1, 2, 3, 4, so on, and then these are half a wavelengths, right? Similar over there, okay? So, very, very similar symmetrical analysis here. What is the next thing that we can say? Well, the next thing that we can say is that the wavelength of a particle is equal to the Planck's constant divided by momentum p, okay? For a string wave, we couldn't say that. For a string wave, we said the velocity is wavelength times frequency. Wavelength was velocity over frequency. For a particle, which we are describing as a wave, the wavelength is Planck's constant over momentum, right? So if this is equal to, according to this, the wavelength it must be equal to what? Twice the length divided by n. So you put that over here, twice the length divided by n. So the wavelength must be equal to 2L over n. Let's get an equation for the restricted momentum that this particle can have. It can only have restricted momentum. So cross multiply, we have P is equal to what? This one goes over here, this one goes over here. NH divided by, and then the 2L goes down here. In the n equals 1 state, its momentum is equal to h over 2L. In the n equals 2 state, the momentum is equal to 2h over 2L, which is h over L, and then so on and so forth, right? Now we can come up with the equation for what energies this particle could have. We said the energy is equal to, in this case, it doesn't have any potential energy, right? So the energy is only in the format of kinetic energy, which is equal to P squared over 2m. So the energy is equal to, and then you square this, n squared h squared over, and then if you square the bottom here, 4l squared divided by 2m. Summarize this, we get n squared h squared over 8ml squared. So we can say, sort of, we are coming to a conclusion here, the analysis of a particle in the box, we can say the energy, the allowed energies of this particle in the box are n squared h squared over 8ml squared, depending on what the mass of the particle is, what the length of the box is, what the Planck's constant is, and then of course n can have a variety of values, any integer values, 1, 2, 3, 4, 5, 6, so on, so on. Notice from here, this is a very important statement. N cannot be equal to 0. N equals 0 is not an allowed solution. Okay, why? Because you must be able to fit at least half a wavelength, right? In a string resonance. So just like in a string resonance, you can't have n is equal to 0. For particle in a box, you can't have n equals to 0. This is very different than the analysis of classical physics. In classical physics, you could have a particle in the box, and the particle can just be sitting still, and its energy is 0. It doesn't have any kinetic energy, right? So you could have a box like this, you could have a particle there, and the kinetic energy can be 0. According to quantum mechanics, even if it's the lowest possible energy that it can have, it's still not 0. It still has a minute amount of energy, okay? Now, what happened to our wave function? Remember, the wave function we had was equal to a sine of pi x over L. Okay? Now, what's the other thing that you have to do to the wave function? So far, here's what we did. We got the wave function. We required that it be continuous. Those are called boundary conditions. Then we solve for the allowed momentum. We solve for the allowed energies. The next thing to do is to require the wave function to be normalized. Okay? We have to normalize it. So what does that mean? Okay? Here's what we have to say. We have to say that the probability of finding this particle between the two ends of the box has to be 1. Right? The probability density of finding a particle within a certain amount of with a certain uncertainty dx is known as is equal to the wave function squared. Okay. So the probability density is the probability of finding the particle within a certain area at a certain spot. Okay? So right now we're only talking about a linear motion, so we only have the wave function as a function of x. In two-dimensional, it would be function of x and y, so it would be probability density in a surface area, right? The probability of finding the particle in a surface area, and then in 3 dimensions, it would be the probability of finding it in up, down, and to the sideways, right? In a little cubic volume, okay? So now, here's what we're going to do. We're going to multiply this by dx, multiply this by dx, and then integrate it, okay? Now, you might say to yourself, why is the probability density equal to the wave function squared? Why is it not just equal to the wave function? Well, one way that you can visualize this is that the wave function itself can have positive values and negative values. So it wouldn't make sense for a probability to be negative, okay? The other way you can see this is that when you learn more about this, you actually learn that the wave function can be expressed as a complex number, okay? And in a higher level quantum mechanics, often they express it as e to the I kx, and it becomes a complex number. So it turns out that the wave function itself is not what gives the particle a meaning, it's the wave function squared, okay? That becomes a real value, and then the wave function squared is proportional to the probability density of finding the particle. Now if I multiply this by the thickness dx, I get the probability of finding a particle at the position x with an uncertainty of dx, okay? My uncertainty in its probability is dx, okay? So here's what we mean by normalizing it. If you integrate this 0 to L, that probability should equal 1, okay? So that's what it means to normalize the wave function. So it turns out that you say 1 is equal to integral 0 to L, and then you square this, a squared sine squared pi and x over L dx, and then you set it equal to 1, and then you get a value for the amplitude, okay? I'm not going to go through the math of that. What ends up happening is that the amplitude turns out to be equal to square root of 2 over L, okay? And then that normalizes the wave function. Now we are finished with the analysis of the particle in the box. We can now begin answering those questions. Okay, so let me erase this portion of the board.